Now we are going to look at another example of the combinational circuit, and this time we are going to look at a multiplexer. So we can define a multiplexer as a combinational circuit that select binary information from one or many input lines and direct it to a single output line. So it is a multiple input single output system. If we are to draw the block diagram of the multiplexer, we can have a single output, let's say Q naught, and we can have multiple input where I naught, I1, I2 all the way to I of n, they represent the inputs and the Q represent the output. As an example, I will give you a scenario. If we have a telecommunication system, and we all know what is a telecommunication system, and this system is responsible for directing and transmitting of signal from the transmitter to the receiver. So imagine if we have many people. Imagine if we have a caller. We can say caller 1, caller 2, caller 3 all the way to caller 4, and this is you as a receiver, and you have your mobile phone, and those 4 callers are trying to call you at the same time. So when t is equals to 0, at time t is equals to 0, all of these press the option to call you. So all of them are calling you at the same time, and you on the other side, you have only one mobile phone which have the phone number which identify you, and those 4 people are calling you. So how can this telecommunication system manage the call between the transmitter, which are the people that are calling you, and you are the receiver? So a scenario like this can be managed using the multiplexer. So a multiplexer is responsible for selecting one call at a time. So it is a process of transmitting a large number of information over a small number of channel or lines. So in that case, we can say the telecommunication through the select lines will now responsible for selecting which of the 4 callers to call you at that instant when t is equals to 0. So depending on the select line, it may select caller 1 to allow transmission to your mobile phone, while it will disallow caller 2, maybe caller 3, and caller 4. Or it can select caller 4 while it disallow caller 1, caller 2, and caller 3. So in a case like this, when we want to transmit information to the output of a system based on multiple input, so we have multiple input and single output. So we normally have the select lines, which now will select which of these multiple input will pass to the output of the multiplexer. So this is the working of a multiplexer. The information at the input can be specified using 2 to the power n, where the n is the select lines. For example, if we want to know the number of input of a multiplexer, if we have the multiplexer which is called the max, if we have example 1 select lines, we can say 1 select lines. So that means to know the input, we have 2 to the 1, which should gives us 2 input. So we can have input 1 and input 2. So depending on the select lines, if the multiplexer has a 1 select lines, that means it will have 2 input, and we all know that the output will always be 1. An example, if we have a multiplexer and now we have 2 select lines, S1 and S2. So 2 to the power 2 will gives us 4 inputs. So we all know that this multiplexer will have 4 input, I0, I1 all the way to I3. And also if we have 3 select lines, then we all know that the input will be 8 and the output will be 1. So we can specify it by having a max, having 1, 2, and 3, select 1, select 2, and maybe select 3. So we can have I0, I1 all the way to I7. So we have only one output. So you can have many number of input, and this input must come along with the select line, because this select lines will specifically select the type of input that can pass through the output at a time instant. And since it is a combinational circuit, from our previous video we defined that we can represent a combinational circuit using the expression, and this expression can be known as a Boolean algebra, and we can represent by using the circuit diagram. And thirdly, we can represent using a truth table. So when dealing with most of digital system, we can use those expression, the truth table and the circuit diagram, to show how the circuit will operate using the binary, which is the ones and the zeros. So this is very important. So we will look at the example of 2 by 1 multiplexer and 4 by 1 multiplexer. So in some case they normally wrote in this term like 2 by 1 max, you know that it is a multiplexer with 2 input and 1 output, or 4 by 1 max, you know we have 4 input and 1 output, and so on. So a 2 by 1 multiplexer, the circuit diagram can be drawn as follows. We should have I0, which is the input to the AND gate, and we have a NOT gate which is connected to the input, and another AND gate which is connected to I1, and we have the select lines, and we have the output which is connected to the OR gate, so it gives us Q0. So this can be our select line, let's say S1, and the symbol of the multiplexer can be given as we have I0, I1, and the select one, and we have the Q0. So this is our circuit diagram and symbol for the multiplexer. So we can find the response of the system such that Q0, which is the output, and Q0 will be I0 or I1, because due to the select line it will select either I0 to appear at the output or I1 to appear at the output. And remember that the input of the system is the binary, and the output is also binary, and those binary, they carry information. So when we talk about binary information, we are talking about the data. So if we want the information from I1 to pass through to the output, then it depends on the select line, or either I1 to pass through the output, then it also depends on the select line. And this select line is also represented in binary. That means it has a state 0 or 1. So let's say I0 carry the information or the data which says hello, and I1 carry information such that how are you? So we can say Q note is a speaker. For this example, we can say speaker. So depend on which we want to listen, for example, hello or how are you, then it depends on the select lines. So let's see, if the select line is 0, then this 0 will appear at the input of the NOT gate and it will be inverted. So it will be 1 appearing at the first AND gate, and from the second AND gate it is 0. So if we have information such as I1 trying to pass through, so this information can represent 1. And 1 and 0 will give 0 at the output. So we all know that no information such as how are you will pass to the speaker. However, the hello will pass through because from the first AND gate both input are high. So the output will be high. So this one will pass through Q node. Now let us see if the select line is 1. That means 1 will appear at the input of the second AND gate, and 1 will appear at the input of the NOT gate, and the output will be 0. So if we have information 1 at the first AND gate, the output will be 0. And it will only allow the information I1 to pass through the output. So we can have I1 at this output of the second AND gate, and I1 will be the output of the entire multiplexer circuit. So we can now be able to see that when the select line is equals to 0, we have I naught which is equals to Q naught. That means the output will be the input I naught. So whatever information such as hello will pass through the output. And when we say the select line is equals to 1, then we have I1 which will pass through the output Q naught, which is the how are you. So we normally control which input will appear at the output by controlling the select lines. So the select lines become our control. If we want to pass hello to the output of this multiplexer circuit, we normally control by applying a binary 0 to the select lines. So by then, the speaker can be able to produce the word or information hello. And when we want how are you to pass through the multiplexer to the speaker, that means we normally apply a binary of 1. So let us describe using a truth table, and we can say that the input, let's say the select line. The select line is our input and our output is Q naught. So when the select line is 0, the output will be I naught. When the select line equals to 1, the output will be I1. So this can be our simplified truth table that represent the operation of the 2 by 1 multiplexer. So this multiplexer have many applications where it is important when we want to select a single data line from a multiple input to pass through the output. So from this truth table, we can derive the algebraic expression for the 2 by 1 multiplexer. So we all know that the expression can be the output, which is Q naught, which will be equals to, from the circuit diagram we can derive the expression such that for the I naught we normally have the select lines. So we will have I naught dot S1 bar plus I1. From this diagram we can derive from this I1 dot S1. So this can be our expression. So this plus represent our OR gate, and this expression represent the 2 AND gate. So we normally derive the expression from the circuit diagram, and it is also related to the truth table. So this is a 2 by 1 multiplexer. Now let us look at 4 by 1 multiplexer. So what is a 4 by 1 multiplexer? So already you can be able to picture the 4 by 1 multiplexer. They have the same operation. The only difference is that it will have 4 input and multiple output, and it will be governed by not only a single select lines but two select lines. Now let us draw the circuit diagram of 4 by 1 multiplexer. So we normally have 1, 2, 3, and 4 AND gate, which correspond to I0, which correspond to I1, which correspond to I2, and we have the I3. And we should have two select line which correspond to S0 and let's say S1. So these two represent the select lines for this particular 4 by 1 multiplexer. So this one should be connected to this one and this one. So the dot represent the point of connection, and this one can be to this one, and this is the point of connection. This is another point of connection, and we should have this another point of connection. So all of this will be connected to the OR gate, which will now gives us Q0. So this is our 4 by 1 multiplexer. So we can simply describe the expression. However, the symbol is quite simple, such that you have multiple input I0 all the way to I3, and Q0 is the output. So we have the AND gate which have multiple input, and this time we have 3 input to each of these AND gate and 4 input to the OR gate. So let's see when the select line is 0 and 0. So when both input are 0, that means when we invert, this will be 1 since it is inverted, and this line should also be 1. And from these select lines S0, we should have 1 and 1 at this input. So all the rest will be 0, such that this line will be 0 and this line will be 0. We can have 0 here and 0 at this line, and also 0 at this line. So here I3 will be 1, we can say I3 will be 1. However, this one will be 0, and we can see that only I0 will be appearing on the other side of the AND gate. So we can see that the output will only accept one of the input one at a time. So from this AND gate, since we have 3 input, in order to have high on the other side, we should have all the input must be ones. In order to have the output I on the other side, if one of these is having a binary of zeros, then the output will be low. The output will be I only if all of its input are high or ones, or having a 5 volts at the input. So from this we can now be able to see that Q0 will be I0. So the output should be I0. How about when we have the select lines S0 is equals to 0 and S1 is equals to 1, what will happen? any variable in the S node will stay unchanged except for these variables. So we can have, when we have 1, we should have 0 here, and we should have 0 here, and we should have 1 here, and we should have 1 here. So how can you see this coming? Because here we have both of these are high, that means I2 will pass through. So we can have I2 when we have the select line S1 is equals to high. That means we have I2 pass through the other side because all the condition of the third AND gate is true. We have 1, 1 and the information I2, so it will allow I2 to pass through. Now what will happen if we have this is 0 and this is 1? What will happen? So we will have this portion 1, this will be 0, this will be 0, and this will be 1, and this portion will be 1. So when we have 0 here, this will be 0, and this will be 0, and this will be 1, and this will be 1. So we can see that these two conditions for the second AND gate is true. We have 1, 1, and the input I1. So we should have I1 at the output. So in that case, we have I1, which is the output when the select line is equals to 1 and 0. And finally, when we have both the select line is high, that means we have 1 and 1 here. So we should have this portion will become 0, this will become 0, and this will become 1, this will becomes 1, and from S1 we can see that this portion will becomes 1, this will becomes 1, and this will become 0, this will become 0. So we can see that only the fourth AND gate is having all binary state of input 1 at the input, so the output will be I3, while the rest we have some 0 as an input, so the output will be low. Therefore, finally we can see that the output will be I3 when the select line is 1 and 1. So we can see that the control, which is the S1, is responsible for controlling each of the output at an instant when we have the select line. If we want to pass this information to the output, we normally control by selecting 0, 0 at the input of the select line. However, if we want to pass I1, we simply apply 0 and 1 at the select line, so we should be able to pass I1 to the output. So from this, we can now be able to finally describe the Boolean expression. And Q naught is equals to, let's see, I naught is equivalent to S naught S1. And since it is 0, we can say bar bar, because when we apply 0 and when we invert, it will becomes 1 1, and plus the output I naught, it will be 1. And from this truth table, we can see that I2 and we have S0 bar and S1, because this one when we inverted and it becomes 1, from the multiplication we have 1 and S1 is equals to 1, and the input I2 is 1, then the output is simply the I2. And we have I1 and we have S0 and S1 bar. And finally, the last, we should have I3 is equals to S0 S1. So this expression can be derived from this truth table and also can be derived from this circuit diagram. So all of these are interrelated. So with this example, we can see that by looking at 2 by 1 marks, we can simply go to 4 by 1 marks, and then we can have 8 by 1 marks, and we see that due to the control, which is the select lines, we normally have one select lines, and in here we have two select lines, and here we can have three select lines, and so forth. So depending on how much select lines we have, or how many input to the multiplexer will have, they all will correspond according to this equation 2 to the power n. So we can have many input to a multiplexer, and then depending on the control, we can select which of this input will pass through the output. So I hope with this video, you can be able to understand what is a multiplexer and how can we control the input based on the select lines. So there are many applications of a multiplexer that can be found in a communication system, a computer system. Later on, we will look at some of the example and how they are used in a digital circuit. Therefore, to summarize what we have discussed, by now you should be able to know what is a multiplexer definition, and you can be able to represent the multiplexer in terms of the truth table, the expression, the Boolean expression, and the circuit diagram, and the circuit symbol. So what we looked at previously is 2 by 1 mux and 4 by 1 mux, and we relate all of them to the definition of the multiplexer, truth table, Boolean expression, the circuit diagram, and the symbol.